So I'm not, here we go, recording. Okay. The quiz on As You Learn. So it occurred to me that the answer key was wrong on two of them. The one where it wanted the min and the max, it was the answer key that I had pulled it off of gave the X value instead of the Y value. So I changed the answers on those and regraded it. So you may see a change in grade on your end. So if you want to, you can check back on that. The other thing was I have to go through and individually grade the ones where you answered. So like, As You Learn is very picky sometimes, where if you put, like -2 to 2 and you put a space after your comma and I didn't, it counts it wrong. So I have to go through and try to account for all of those kinds of things. And I mean, it'll just take me, I'll have to go through and check them, just like it took me however long it did to grade your test. I mean, your tests were graded, but then I had to scan everybody's 3 pages, upload it, send it in an email, and now I'm doing that for my pre-calculus classes. So it just takes time, and time is, you think you have a bunch of it now, but when you try to do a bunch of, like 5 different things at once, it just gets away from you. So I get it. It's clear that some of you are going to have to push yourself a little harder to do your homework on the deadlines that have been posted. I mean, it's not just a free-for-all, do it whenever you feel like. You're still going to have to adhere to deadlines, because I think the 4.2 homework, I think it cut off last night. And so now you've got some guided learnings that are up. Let me see those. Some guided learnings. Well, I guess for the 4.4, I think the 4.3 one cut off also. And I have to look and see if I have one for 4.6. But I mean, it's not any more homework than you had before. It's just you have all this other stuff mixed in with your life that you're having to juggle. And I think those of you in your 18 to 24-year-old world are going to grow up a little bit in this time frame with your ability to pace yourself and push yourself, because now that you don't have that class to walk to and that class to run across campus to, it makes it a little harder. So we'll get through it. Some of you are going to have to up the effort a little bit to make the most of your grade. But let me know if you have questions on anything. It seems for the most part, I haven't checked your class, but if you uploaded work from, and I'll email you if this is you. I had some pre-calc students do this. If you use a newer iPhone and you upload the photo directly from the phone, it's this weird HEIC file, and I can't view those. So if you've uploaded something that I can't view, I will let you know and you can send it to me through an email. The time amount that you were given was plenty of time to have done that quiz for the content. So if you got to your 45, because I think you had 45 minutes, right? If you got to the end of that, JPEG is fine, yes. If you got to the end of your 45 minutes and you didn't have time to upload it, then you didn't know what you were doing on your quiz, because there's no way it should have taken you that long to do the actual content. If you sat down and you were prepared, like I hope most of you were. But like I said, I'll go through and I'll regrade and we'll talk about them, but we're not going to talk about it today. But I just wanted to let you know that some of you that it initially marked wrong, like the numerical ones, go back and check it, because now they might be right. Okay. Does anybody have questions before we get started on anything class related? You want to type it out? You want to say it out? Anything? You're good? I'm glad that this one is going smoother than some of your, I mean, I wish all of your classes were going smooth, but there were a lot of comments that said this one was a little bit smoother transition online than some of your other ones. So you got to realize a lot of people at that university have never done online. So they're struggling. But my struggle is time with kids who have to cut out letters of the alphabet with scissors and put them in order and write the life cycle of a jaguar. So, that's my struggle, is trying to juggle all of that. But thankfully we have teachers that are working around my commitment to you and their availability. So after this, I'm going to do reading group with 3rd grade. So yeah. I did change office hours. I think I sent that out to your class. It doesn't affect your class. It just affects the office hour availability. A lot of people indicated 2 to 3, 3 to 4, maybe more optimal time. So, I mean, if there's a time that you can get on and you want to see if I can video with you, all you have to do is shoot me an email. But email is not chat. So give me 20, 30 minutes to check it, because sometimes it notifies my phone and sometimes I don't know what it's going on. It's like its own little, just checks it when it wants to. And I'm not going to sit there and refresh my email every 5 minutes. It's not reality. So we need to keep going. Today I thought I would just wrap up some of the, well, not really wrap up, it's really continuing. 4.3 looks at increasing, decreasing tests. 4.4 started introducing increase, decrease, minimums, maximums, concave up, concave down, and 4.6 sort of like throws it all together. And like the quiz that I have on this portion, it's like one question and it has like 20 parts. It's like, what's the first derivative? What's the critical numbers? Where does it increase? Where does it decrease? What's the minimum? What's the maximum? What's the second derivative? So it's like this one sheet of all these questions that pertain to this one function, but you have to use calculus. So I thought, oh, and I'm gonna not what's the word? Embarrass you, Mary Gray, but I am 100% thankful that we video chatted yesterday, because I got my iPad to work, because I had to make it trust the computer. It had some trust issues. I don't know where Haley is. They had trust issues at school. It had trust issues, so I had to like reset my whole iPad and make it trust my computer again, because it would not show my iPad. And it was not a good afternoon, but I finally figured it out, and here we are, and it still works this morning, so we're good. I could not believe that it did that, so thank you.
That's not embarrassing. It's okay.
Yeah.
But yeah.
No, it really would have made for a bad day if this morning is when I checked it and then that's when it did it. But so I was like 7:30 this morning hooking my iPad up to my laptop, doing a Zoom session just to make sure it would share it. So we're good. So 4.3, 4.4, and 4.6, they really run together and repeat a lot of the same content. So what you pull from those sections is you have this, it's called the increasing, decreasing test, which we looked at before. But basically it says if you have a function and you can find those critical numbers from the first derivative, anywhere that the first derivative is negative, then the original function is decreasing, and anywhere that the derivative is positive, the original function is increasing. So you've had homework due on this already, and the critical numbers are sort of some of the hardest things to find, especially if you have square roots and fraction functions, your rational functions, and there's a lot of different types of functions that you can have. I mean, the unit circle values come back in this chapter, so you need to be familiar with that or have it in front of you so you can see. And what happens, like we made these little charts, and you've got these numbers, and it was positive to negative to positive. Well, what's going to happen, F prime, F, is if you have an increase that switches to a decrease, then what happens graphically is you get a local max as long as there's not an asymptote there. Hey, Carter, can you calm down with the Legos, dude? Because it's loud. You're Legoing loud, I can hear you. Okay, sorry. If you visually have a decreasing function and around a critical value it switches to increasing, as long as there's no asymptote there, there's no domain issues. If you decrease, then you increase, what you're going to have is a local minimum. So this is where 4.4 picks up, and it adds your ability to know where those minimums, and they're local, because a lot of times they're polynomial So it'll increase, then it decreases, then it increases. And not only will you tell where it does the increase and decrease, but you'll also use this to figure out where it has those local extrema. So that's using first derivative. Where second derivative comes into play, it's used to figure out concavity and also points of inflection if there are any. And then in section 4.6, it sort of looks at functions that have asymptotes, and there's critical points, but maybe there's not a point of inflection. So between today and tomorrow, we'll look at a bunch of different examples. But the second derivative, it's not the second derivative test. The second derivative test is used for minimums and maximums, and I can write that out for you on another day. But this is testing for concavity with the second derivative. And what this basically says is we'll do the same thing. We'll find where the second derivative is 0 or undefined. They're kind of like critical points for the second derivative, but anytime your textbook refers to critical points or critical values, they're always for the first derivative, but technically you find them for the second derivative too. If you can find values where the second derivative is 0 or undefined and do this little test interval, the same like we do up here for increase and decrease, you'll do the same thing for the second derivative numbers. And whenever the second derivative is negative, the original function is concave down. And wherever the second derivative is positive, the original function is concave up. And anytime you switch from concave down to concave up, you create a point of inflection, and those are the ones that you have to be able to give for answers on your homework. And usually, like with the minimums and the maximums, I found that this textbook, it can ask for the X value, or maybe it'll ask for the actual maximum Y value or the minimum Y value. And with points of inflection, it asks you for the actual XY point. So you have to be really careful, especially in Sapling with the homework, which one it asks you for, because it's really easy to mess that question up. And if you do mess it up and you realize that's what you did, shoot me an email and I can reset it. It's not really a problem. It takes like 2 seconds to reset a question if I know which one it is. So all of this being said, the big picture is first derivative tells you information about increasing, decreasing, local mins and maxes, and the second derivative is going to give us information about concavity and points of inflection. So you can answer 10 to 15 questions on one function just based off of its derivative information. But it does all require that you understand how to set that derivative equal to 0 and how to find the critical numbers for each of those derivatives. And for some of the trig ones, it gets a little tricky. Quotient rule, product rule. Just depending on the nature of the function, it makes the question harder. Okay, so anybody need to stop me for a minute before we do some examples? No, you're good. Okay, so I had, which one did we do? So I have a couple that have trig in them. But I want to make sure that we do ones that include, make sure nobody's typing anything. That's a product rule. I guess I could do a really easy one. Well, that just doesn't seem very easy. Oh, that one might be good. Let's do this. I like to start with polynomials just because they have real defined ups and downs, and sometimes they're nice integer answers. So we'll start with this one. So again, this is it's stuff from 4.3, but it also blends with 4.4 with the minimum maximum concavity. And that's kind of why the homework is all chunked together. And I don't remember what the due date said it was. April 1st. I'll probably give you maybe like till Friday or Saturday to do it so you can prep for the quiz adequately over the weekend. So here's a function. X cubed minus 6x squared plus 9x plus 30. Okay, and again, the realization, I understand you can graph it and you can pull a lot of information from the graph, but your assessments will require you to show the use of calculus, and then you can graph it to verify things that your calculus has shown you. Okay, so for this question, we're going to do where it increases, where it decreases, any local minimum, any local maxima, if it has more than one. We'll also figure out where it is concave up, where it is concave down, and any points of inflection. So just to sort of give you those are the things that we're going to try to pull from this cubic that will have all of those things. Okay, so to get the increase, decrease, min and max, that's going to use first derivative. So we'll just start with first derivative. So first derivative, using just power rule on each of the terms. You've got a 3x squared minus 12x plus 9. And to find those critical numbers, we'll set it equal to 0. And it's a nice quadratic. We can factor it most likely. Not if you want to use the quadratic formula, you can. I just feel like it's a lot more work than you need to. We've got a 3x squared minus 4x plus 3. And that factors into x minus 3, x minus 1. And once you get, if it's a polynomial, I think there's some of your homework questions had 4 terms and you had to factor by grouping, and some of you may have had to review that, or maybe you used a graph. I'm not really sure because I didn't really have a lot of questions on email over the weekend. But if you set each of these equal to 0, once it's a product, you're allowed to do that. So then you get an x value of 3 and an x value of 1. And these are both in the domain of the function, so they're considered critical. And in section 4.6, we have some that show up that they're not necessarily critical, but we have to use them in our test. But as far as reporting what the critical numbers are, it's 1 and 3. Those are the things that make the first derivative 0. Nothing will make it undefined. So then if we test for increasing and decreasing, so for increase, decrease, and the determination of any of those local minimums and maximums are called extrema if you pluralize it. So I've got a 1 and a 3. So I'll make space. There's 1, there's 3. So those are the x values. And again, these are critical numbers, and then you're testing everything in between and around them. So I'll go 0, I'll go 2, and I'm going to go 4. Again, it's just any number less than 1, any number between 1 and 3, and then any number greater than 3 is what goes in those boxes or those test number line, whatever it is you feel like drawing. And then we're going to look at the sign of the first derivative, whether it's positive or negative. Again, we did this last week, and I'm not interested in the actual function value, but whether or not it's positive or negative. So this would be a really easy representation, the factored form, or if you want to, you can go up to the original one. It doesn't really matter. So if I plug in 0, if I plug it into like the original first derivative, I get 9, but more importantly, it's positive. If I plug in 2, again, I'm looking at any number in between 1 and 3. 2 is just the easier integer choice. If you plug 2 in, and I mean, you can envision it plugged in here for the x. 2 minus 3, that's negative. 2 minus 1, that's positive. That product, negative times a positive, that product is going to be negative. So the sign here is negative. And if you plug in 4, again, just, you don't have to, if you want to literally plug it in, you can. But if you can envision the 4 plugged in, 4 minus 3 is 1, 4 minus 1, everything is positive when you plug in 4, or really any number bigger than 3. When you plug it in here, that product is going to stay positive. So the derivative is positive. And what that means when you look at the function, so f of x, I guess it's sort of like behavior. is in this interval where any x value was less than 1, the actual function is increasing here. Any number between 1 and 3, so like any x in between 1 and 3, or from 1 to 3 in an interval, you have that it's decreasing. And any number greater than 3, or if you want to go 3 to infinity, the original function is going to be increasing because that's where the derivative was positive. And there's no asymptotes, there's no breaks in the graph, it's a straight polynomial. So if you can envision an increase to a decrease, that creates a local maximum at the x value of 1. And if you go from a decrease to an increase, that if you, again, just envision it, it's a minimum at the x value of 3. So you're increasing, then you're decreasing, then you're increasing again. You're going to get a local min and a local max at each of those changes. Okay? So as far as answering where it increases, it's increasing everything up to 1 and everything after 3, and it's decreasing in the middle from 1 to 3. And there is a local minimum and a local maximum. So these are the x values, minimums at 3, maximums at 1, but depending on how the question is phrased, you could say the local minimum occurs at x equals 3 and the local maximum occurs at x equals 1, or it might ask you for the y value. And in order to get that, it's the y value from the original function. You don't plug it back into the derivative. So this is like going all the way back to the original function here, this x cubed, but that's where you would get the min and the max. If it asks you for the y values, if it asks you for the point, you put the coordinate point. If it asks you for the x value at which it occurred, you can put 3 and 1. But if it asks you for the value of the minimum or the maximum, then you have to plug the x in and actually get the value from the function. So like this would be, if I plug 1 into f, I think you would get, what, 1 cubed minus 6 times 1 squared plus 9 times 1 plus 30, whatever that is. I think it's 34. That's what I got when I did this the last time. And if you do the function at 3, like 3 cubed minus 6 times 3 squared plus 9 times 3 plus 30, you end up getting 30. So again, these are just the y values of those min and maxes. So the local, let me zoom back into here so you can see this. So the local min that happened at 3 corresponds to a function value of 30. Again, that's the y value. And the local max that happened at x equals 1, the local max is going to be the number 34. So again, it depends on how it asks you to give the answers, because you have a minimum point at the point 330 and a maximum point at the point 134. I mean, it's just, we'll look at a graph and I'll show you, but just please pay attention to what the directions ask for, because I would be more inclined to ask you for the y value or the point. And I know that you can pull that from a graph, but your calculus has to match it. So that's half the question. Does anybody have questions on those? Where any of the numbers came from? Process. Everybody's okay? Can't see your face. It's like the number one thing I miss being able to do is see your face and your expressions as to whether or not you're getting this. Okay, well, I'm just gonna assume. I hate to assume, but you don't talk, I don't know. So we found that stuff. Now we need to find information about its concavity, because I mean we have it increasing, then decreasing, then increasing again. So part of it's concave down, part of it's concave up, and somewhere in the middle, there's an inflection point. So in order to do that, let's see, we've got, let's see, first derivative. I wonder if I can copy that. Will it let me copy that today? Probably not. I don't know why it would. I thought that would just, hey, there we go, copy. Will it paste? I don't know. Thought that would work, but surely it wouldn't. I don't know why I thought it would. Okay, okay, so original function with a thicker pen is x cubed. You can keep going on your notes. I just ran out of virtual paper. The first derivative, 3x squared minus 12x plus 9, and now we're going to use second derivative. All right, so second derivative, this is for concavity and points of inflection. So the second derivative we get is, I guess just power rule, 6x minus 12. And if we want to get, I call them the critical numbers, but anytime your book references critical numbers, it's just the one for the first derivative. So we're trying to figure out where this is 0 or undefined. And if you add 12, I like them when they get the second derivative. A lot of times they're easier. You just get the x value of 2. So 2 is where the magic may happen for this picture. So then we'll use the x value of 2 and test concavity. So again, it's this little chart thing. Here's your 2, but now we're looking second derivative. And that'll tell us the behavior of our original function. So just like before, you need a number below 2 and a number above 2. So I'll just go with 0 and 3. Made a weird chart here. So again, this was just a number below 2, and this was a number above 2. 2 might be a point of inflection. I'm not really sure, but we'll check it. If you plug 0 into, again, we're going into second derivative here. And I'm only interested if it's positive or negative. So if I plug 0 in, 6 times 0 minus 12, then this is negative. That says negative, I swear. Negative. And if I plug 3 in, again, we're just taking, that's a pen. We're taking the number 3 and we're plugging it into second derivative here. And if you do 3, 6 times 3 is 18. 18 minus 12 is positive. Then we changed from concave down. Negative second derivative means concave down function. And then it went to concave up. So at 2, there's a point of inflection because your second derivative signs change. So that means your concavity changed. It went from down to up, and 2 is a point of inflection. Okay? So it's concave down on the interval negative infinity to 2. It's concave up on the interval 2 to infinity. And then here is where you have to be super careful in sapling, because when it asks you for the point of inflection, you can't just put the number 2. You actually have to give the whole coordinate point where it changes concavity. So it'll be 2 comma number, and that number will be the function, like the original function value when x is 2. So that's all the way, let me get my highlighter action going on here. That's all the way back up here with this original function. Because again, any minimums and maximums and points of inflection occur on the actual function, not on the graphs of the, I mean, they're on the graphs of the derivatives, but that's not where the inflection point is. So if you plug 2 in there, like 2 cubed minus 6 times 2 squared plus 9 times 2 plus 30, you end up getting the number 32. So it increases to a max, it decreases to a min, it increases after that, and in the middle of those two, it changes concavity, and that's all of this information that we found. Like concavity, point of inflection. That's like a 6-part, 6-question test. Actually, 7, 8. You could probably make it 9 questions just from this one problem. Okay, but first derivative gives you certain information. Second derivative gives you all this concavity and a point of inflection. And if we graphed it, you could verify it, which is what your graph is supposed to be for, not to do all the work for you. It's kind of lost its purpose over the last 15 years in education. Here is our function. We wanted to graph it. See, it increases, then decreases, then it increases. And you could graph, there are your points, right? There's a local max at 134. There's a local min at 330, which is what I think we wrote before. It increases up to that max. It decreases in between. It increases after that. It will be harder when it has trigs and logs, but we'll do some. I promise you, Jeremy, we'll do some. I just need you to understand the concepts to begin with about what we're finding. What about, so the point of the minimums and maximums are pretty easy to visually see and graphically find, but the points of inflection won't be as in your face a lot of the times. So we found it to be, what did we say, 232? And that is the point that is exactly in between where it changes from concave down to concave up. And sometimes it's nice and integer based like this, and sometimes it's like the cube root of 1/4 or 3 pi over 4. It just depends on the function. But the point is, it's where the second derivative had a critical number, and it's where it changed concavity from down to up or up to down. And we're using calculus to find that exactly, not just, you know, I don't know what it is, but I'm going to zoom in and ballpark it. You can't ballpark these. Calculus gives us the tools to find exactly what the numbers are. Okay. And section 4.6 does more of this, but I think the functions get, I don't know, a little harder. I have one. I guess we could do a couple trig ones, unless somebody had a question on this one. This one wasn't. The polynomial ones are easy, which is, I think, what the first quiz had you do was one with a polynomial, just because of the nature of it's just a little bit easier. But the process is the same. But again, the question, what you're exactly right, what will make them hard is your ability to do all of these functions. I'm seeing I had, there's one. I was trying to think if I had another one. That's a point of inflection one. Let's see. Chat. So looking at a graph, Tori, is stuff I think that we looked at last week when I put up some of, where did those slides go? 4.4. These guys, I posted it, and I posted it in its entirety with answers. So I don't know how many of you looked at this 4.4 handout. I mean, I couldn't do all of them, but what it gave you were pictures. And so there's actually a quiz question that used where it increased and decreased, but like for this one, is this what you mean, Tori, on these? See your chat? Yes, okay. So yeah, on questions like this, when it gives you just the picture, there's no actual function. You're just using the information that we talked about. So if you notice, this is a graph of the derivative. This is not the graph of the function. So if you were asked, what are the critical numbers for the function, this is going to play on your ability to know it's wherever the derivative equals 0 or is undefined. I mean, that was also a quiz question, right? So looking at this derivative graph, you can see that its zeros are -2 and 2. So that is going to be critical numbers for the function, because that's where the derivative is 0. So again, it's using the same definitions of what they are. It's just applying it to a graph without any kind of function, like equation to look at. Okay. Chat box. I wish this would just stay up. Okay. The increasing part. Okay. Here, where it says, where is the function increasing? Well, you don't pick where the derivative is increasing. The original function is increasing wherever the wherever the derivative is positive. So positive world on this graph is up here. That is positive first derivative existence. The whole upper part of that graph is where the derivative is positive. So anywhere on those intervals, that's where your original function is increasing. The decreasing is going to come wherever the derivative is negative. I mean, that's what we do when we pull the chart and we figure out where it's positive and where it's negative. So anything down here is graphical representation of negative derivative answers. So it's decreasing. I'm going to erase those because they got a little busy there for a second. It's decreasing everything under -2 because that's where the derivative graph is negative. Anywhere the derivative is negative, that's where the function is decreasing. Anywhere where the graph or the derivative graph is positive, that's where the original function is increasing. And it's really all of this, except you could put -2 to infinity, or I have seen your textbook break it up and go -2 to 2 and then 2 to infinity, because technically at x equals 2, it's neither positive or negative, but I would take all of that if you wanted to put it. But I think what do you use? Sapling breaks it up, because at 2, it's not really positive because 0 is neither positive nor negative, but I would be okay with either one. Okay. And then to answer these other questions, at what numbers, if any, does f have a minimum? So again, if you go back to wherever that paper was, the chart, not that. This one? We were literally just doing it. I don't know where I put that. Here? Maybe here? Really, Natasha? Well, anyway, wherever it had a minimum when it went down and up. So when it went decrease to increase, or when the first derivative went negative to positive. So if you have graphically where the derivative changes from, minimum, you'd have to go down and come up. So anytime it changed from negative to positive, you would have a minimum there. So do you see here, the derivative is negative, and then here the derivative is positive. So at x equals -2, there is a local minimum because the derivative is changing from negative to positive. The only time you would have a maximum, at what numbers does it have a local maximum? This is only going to happen when the derivative changes, because again, you'd have to go up and come back down. So if your derivative changes positive to negative, you'd have a maximum. And in this case, nowhere does the graph go from positive world into negative world. So this one, for this example, would have no maximum for the original function. But it uses all of that information from that box and the definitions of where it's 0, where is it positive, where is it negative, where does it switch, increase to decrease, decrease to increase, or positive to negative. And there are, I don't even know, there's like 10 or 15 different function pictures that I did on this handout, and I posted them all in As You Learn. If you haven't looked at them, I would strongly encourage you to do so. And I can show you another one. I mean, here's, I was trying to find one that had a little more up and down. Well, that one's not so good much. And nobody's chatting yet. Not there. Maybe here. Same set of questions, A, B, C, D, E. I mean, these are just screenshotted from your textbook. If you wanted to know the critical numbers of the function, then you'll go to the graph of the derivative and you'll pull the zeros. So the critical numbers here are -2, 4, and 6. It's wherever the derivative is 0. So the graph of the derivative, any of the zeros, that's the critical numbers. The function is increasing anywhere the derivative is positive, positive being greater than 0. So the derivative exists positively if you go anything below -2 and anything above 6. That's where the positive pieces of the graph live. And f prime is anytime that the derivative is negative, that's where your function is going to decrease. So you're looking from -2 to 4 to 6, all of this under here, this whole piece down here. Again, the 4, I think sometimes it splits up because at 4, it's neither positive nor negative. So sometimes it'll break it up and say like -2 to 4 and then 4 to 6. Or you could just put from -2 to 6. That would be fine for me, but I forget if Sapling will take that. But the reason it's breaking it apart at 4 is because at 4, it's not doing either of those things. It's not doing increasing. It's not positive. It's not negative. It's not increasing. It's not decreasing. Odds are it's a horizontal tangent line with a slope of 0 on the original function. Local minimums, again, minimum. If you go down and come up, that's a minimum. So you need to have any kind of graphical change from negative to positive. So of any of those critical values, do you see where the graph like physically changes from being negative to being positive? I'm gonna let anybody answer that wants to answer that. Any of those critical numbers, does it change from negative graph to positive graph? Let's see what it says. I got a 6. Anybody else think something different? Again, you're gonna have a local minimum if you come down and come up. So derivative means negative to positive. And yes, Brianna, you are exactly correct. Here it's negative, here it's positive, and at 6, it switches from negative to positive. So at x equals 6, you have a local minimum, okay? For a local maximum, again, you go up, you come down. So for derivative world, that means anytime the graph changes from positive to negative in its existence on that graph. So anytime the derivative was positive, so when it went into the negative part of the graph, that is where you're going to have a local maximum happen on the original function. So that one's going to happen at -2. Because here the derivative is positive, here the derivative is negative. So anytime you go positive to negative, you're going to have a local max on the original function, which we don't have a picture of. I don't know what it looks like. I don't know what the equation is, but based off of that derivative graph, you can pull that information. Okay. And then the ones at the end of this pulled the same information, but also started to look at the concavity. So A through E are the same questions. A through E would use first derivative graph. But then when it joined this FGH, these are going to use second derivative graph. And when it asks the question, where is the function concave up? If you go back to those charts that we did, so F is going to be concave up. Yeah, just don't watch videos yet. Give me like 5 minutes. F is going to be concave up anywhere that the second derivative is positive. So if you look at the graph of the second derivative here, see it says y equals f double prime. Buddy, give me 5 minutes. It's okay. It's okay. Sorry. If you look at the graph of the second derivative, where is, that's a pin. Where is it positive? The second derivative graph exists in the positive in those two pieces on the left and the right. So that means the original function is concave up all the way negative infinity to -1, and then everything after 1. And when it says, where is the function concave down? So f is concave down anywhere the second derivative is negative. Again, you're really just pulling the information from those charts and applying it to a graph. So if we were to look where the derivative is negative, it's negative on that lower piece that falls under the x-axis. So from, what was it, -1 to 1, that is where it's concave down. The original function, not the picture, because that's a parabola. Okay, but it's taking the pictures of the derivatives and pulling information for the original function. Does that sort of make sense? Clear as mud. Yeah, I can do one with trig. We have a few minutes left. I have a point of inflection one, or I have, we'll do more tomorrow too. So there were some, I'll do this one. I don't remember what section this came out of. We'll do this one. And we can do more tomorrow. And between now and tomorrow, if you would log on to Sapling and look at your homework, then you can ask questions if you're stuck on it, instead of making yourself, did you see the comment? Get all worked up because you don't know what you're doing at 3 o'clock in the morning. So here is one. I don't know about the second derivative because I just had it kind of the same one. Not really. Okay, I'll do both. If we'll run out of time, I'll do another one tomorrow. So if you had this function, e to the x cosine of x, and you were only looking from 0 to 2 pi. I think some of you ran into these issues over the weekend with your homework. This one is like, where is it increase and decrease? And we could take it further to concavity, but I think we're going to run out of time. So if you do first derivative, this is product rule. So e to the x is e to the x, and then we'll keep cosine, plus the derivative of cosine is negative sine times e to the x. And your job is to figure out where this equals 0. Okay, so welcome back to the questions where it's really great if you know how to factor stuff out. These both have an e to the x, and you're left with cosine minus sine. And once you can pull out things that they have in common, you can set each piece equal to 0. So e to the x equals 0, cosine minus sine equals 0. So if you go back to e to the x, here's e to the x. It's exponential growth. It's never 0. So there's no critical numbers here. Like e to the x will never be 0. So anytime you can factor that out, it's helpful because that portion of it won't give you a critical number. Okay. For the second piece, if you set that equal to 0, there's a few ways you could try to think about this from 0 to 2 pi. You could think, where would, if you did cosine and the sine and you subtracted them, would you get 0? Or you can add over the sine. And you're like, okay, what angles would cosine equal sine? Or if you divide cosine over, sine over cosine is tangent, where would tangent equal 1? Any way that you want to think about this, if you go to the unit circle, pi over 4 and 5 pi over 4, the sine and cosine values are the same. Those are also angles where the tangent value is 1 because the sine and the cosine values divide to give you the same ratio. So your angles here are pi over 4 and 5 pi over 4. Those are your critical numbers. And then you get to pick your numbers in between, above and below, and figure out where they increase or decrease. But I think we are out of time. So I can finish this one tomorrow. But that's a good start. If that helps you, I'd like to think that it would at least help you set it up with the trig one, Mary Gray, that you asked about. I have another one tomorrow we can do with point of inflection. But the unit circle, if you don't have it in front of you, I would have it and pull it out for class tomorrow for lecture. have it for you with you when you do your homework. I gave it to you on the last test, so you're clearly able to use it. But we'll finish this one tomorrow because I think, like I said, we're out of time. Does anybody have other really quick questions that you'd like to ask about? Stop doing this and click here. Just work on your saplings. All I can recommend. Work on it. Email if you have questions. Make yourself a schedule. Just a little here and there will help you get through it. And if I need to reset any of the questions, I can. And if we need to meet outside of the posted office hours, as long as I can swing it with what's going on here, I'll do it. You just let me know, okay? And email with questions and send me pictures of your work. I'm happy to try to guide you in a better direction, okay?
Will we be getting an email if you got our work for the quiz?
You will be getting an email if your work I can't see. So if you don't hear about your work, then you're fine.
Because I have no idea if it worked or not.
Okay. I think you can go back and view your attempt and you can see that it's been uploaded. But
okay.
if you're worried about it, Jeremy, I can take a look at it. But like I said, I'll look through the list. And if any of them are that weird HEIC file, I will send you a personal email to say, hey, I can't see your work. Can you email it to me? And you'll be fine. Okay? Happy Monday. It's a Monday. It's a true Monday. If that's even a thing anymore. All right, good deal. I'll see you guys tomorrow.